pulling two boxes. A 65 kilogram college student from the 1970s stands on an analog bathroom scale, also from the 1970s, inside an elevator car. State the scale measurement when the elevator moves at a constant speed upward, same thing but in the downward direction, or accelerates upward at a rate of 2.4 meters per second squared, or the same rate in the downward direction. This problem is very similar to the tension in the cable for the elevator problem. But what's different? What's very different is the object of interest. The elevator this time surrounds but is not touching the student, so there is no force from the elevator in our problem. What forces do we have on the student? Well, the student is standing on the spring scale here, which is pushing the student up. And we have gravity. Gravity is acting on the student, which is pulling the student down. The scale measurement, which is what we're asking for, what does that mean? Well, that's another word for the normal force. That's the force that the person feels from the scale. So scale measurement, normal force. As the problem is very similar, the math is very similar. The only difference in our free body diagram will be, instead of tension force, which is up here, we're worried or concerned about the normal force that the scale exerts on our object of interest, which is the student. The acceleration is 0 because the student and the elevator, which we really don't care about other than they're both moving at the same rate, are moving at constant speeds. And that's where we get A is equal to 0. Once we have the free body diagram, we can then apply Newton's second law. So the sum of the forces is ma, our acceleration is 0, so the equation becomes the normal force, which is in the upward direction, so it has a positive sign. Gravity is pulling down, so we have negative mg, and since the acceleration is equal to 0, there we go, the vector sum is equal to 0. So we have the normal force minus mg equals 0, add mg to both sides. Over on this step here, it cancels out on the left, winds up on the right, and we have the normal force as mg. We then substitute in our variables here, the numbers. 65 kilogram for the mass, gravitational acceleration 9.8 meters per second squared, and we get 637 newtons. This case, the scale reads the same as the weight of the student at rest. So if the student was in the bathroom, on the bathroom scale, standing on it, it would show 637 newtons. Now the elevator is moving at a constant speed downward. The forces on the free body diagram still point in the same directions. The scale is still pushing up on the student, and gravity is still pulling the student down. Acceleration is still 0. So we look at that picture, so we're going to expect that Newton's second law will give the same equation, so we should get the same result as part A. So here's Newton's second law and the worked out solution with the numerical values, and frankly I just cut and pasted this from part A because everything's the same. Acceleration is the same. The direction of the forces is the same. Normal is still up, mg is still down, algebra is still the same, and we still get the same numbers. So the student's weight is the same, the normal force, what the scale is reading, is the same whether the student is going up or down as long as it's a constant speed, and that also equals the student weight if the elevator is not moving at all. Now the elevator accelerates upward, change its speed at the rate of 2.4 meters per second per second. The forces still stay the same. But maybe you'll remember from the previous problem that the magnitudes of these vectors will be different, of normal and mg, but we don't care for setting the problem up. So the sum of the forces is ma, normal is in the upward direction, positive, mg down, acceleration is up, that's positive. We put mg on the right side by adding plus mg to the left side and the right side, and then we factor out the m, so we only have to multiply by m once to get the answer. And finally, we substitute in our numerical values over here, and see how you only have to multiply by the mass once because we factored it out. That's pretty good. And we get the normal force, which is the scale measurement, of 793 newtons. So the scale measurement is greater than the weight of the student at rest. So in the free body diagram, this vector should be longer than this one, but you didn't know that when you started the problem, so it's okay. We got the right answer, because the important thing is the direction of the vectors. Now we're accelerating downward at a rate of 2.4 meters per second squared. So the free body diagram, the directions stay the same, right? Normal, the scale is still pushing up on the student, mg is still pulling the student down, but the acceleration is in the down direction. And that shows up right here. We do Newton's second law. The left side of the equation is the same. Normal's up, mg is down. But here we have m times minus a, which is going to be a negative ma. We add mg to both sides, so it cancels out on the left, and it winds up on the right. And then once again, we factor out the m. We substitute in our numerical values here. And this time we get 481 newtons. So the scale measurement, or the normal force, right? Normal force and scale measurement is the same. It's now less than the weight of the student at rest. We didn't know that going into the free body diagram, so we're okay the way we drew it, and the math then gives us the actual magnitude of the forces. When accelerating upward, the student feels heavier, right? Because the normal force tells you how much the student thinks the weight is. And when accelerating downward, the student feels lighter. When the elevator is moving at a constant velocity, the student feels the same as if the elevator was not moving. So if you're going from like the first floor to the 100th floor at the Empire State Building, somewhere in between there, you're going at a constant speed, you really can't tell if you're moving or not. Well, I guess you can because you can hear the noise and everything else, but if it was a perfectly quiet elevator, you wouldn't know the difference. So next time you're in an elevator, see if that works. When the elevator starts moving upward, you should feel heavier. When it slows down right before it stops at your floor, you should feel lighter.